Welcome to section 4.7. This is one of my favorite sections in the entire book. Optimization problems. And our objective in this section is to solve applied maximum and minimum problems. So basically what's going to happen in this section is we are going to take that idea of increasing, decreasing maxes and mins, and we are going to apply it to what I refer to as optimization problems, but basically are just word problems. And the reason they're called optimization problems is because in these problems, we're going to have some sort of a structure, a word problem. And our goal is to either to make something as big as possible or to make something as small as possible. And that idea of making something as big as possible or small as possible is where we get the word optimization. Okay? All right, so one of the most common applications in calculus is to determine maximum and minimum values. We did this already. We've done this several times. We took first derivative, turn that into critical numbers, turn that into extrema. And so that's all we're going to do in this section is we're just going to find a function, take a derivative, find critical numbers, make those into extrema, and then pick the one that does the thing we wanted to do. Pick the one that maximizes if our goal is to maximize something, or minimizes if our goal is to minimize something. All right, so let's take a look at an example. Hopefully it'll make more sense after we do that. All right, so here we go. Our job in example number 1 is to find maximum volume. So our optimization goal here is to maximize something. A manufacturer wants to design an open box, so it doesn't have a lid, having a square base and a surface area of exactly 108 square inches. What dimensions will produce a box with maximum volume? All right, so we want to create a box that has an optimized volume, in this case a maximum volume, and the conditions necessary are that it has to be an open box, it has to have a square base, and it has to have a surface area of exactly 108 square inches. Now, luckily for us, someone has drawn us the picture. You'll notice that here and here, that x and x are what's going to make that base be square, but here, they're using a different variable for the height because there's nothing in the problem that says this must be a cube. It just needs to be a, if you want to get fancy about it, a right regular prism, a right rectangular solid. So the base is a square, the height is unknown, and we want to maximize the volume. Now, I learned a long time ago that volume is equal to length times width times height, or in this case, x times h, or x squared h, and that my goal is then to maximize that function. But I can't. Okay, so my goal is to maximize. I don't know why it does that. Maximize volume, but I can't. The reason that I cannot maximize this volume is my knowledge of calculus only allows me to maximize something when it has one independent variable. And this function, if we were to write this more technically correct, would look like this. Because it has two independent variables. It has an independent variable for x and an independent variable of h. The base, the square base dimensions, and the height dimensions. So I can't maximize something that has two variables. I need to find a way to turn this from two variables into one variable. Now, there's lots of names for this approach, but basically what we're going to do is we're going to go back into the problem. We're going to look around for some other requirement, some other restriction, some other characteristic of this box that we can use to find a way to perform a substitution of variables to turn two variables into one variable. Okay? And that is going to be hidden in here. It's the only piece we haven't used yet. And it says that the surface area of this box has to be exactly 108 square inches. And so if I think about that, okay, surface area. Surface area is the bottom plus the four sides. So it's the bottom, which has an area of x squared, plus four sides. And all the sides are the same. They're all x by h. And that has to be exactly 108. And now what I have is I have an equation on those two variables that I'm going to be able to use to do a substitution. Now, at this point, I have two options. I can either solve that red equation for x and then perform a substitution of x, or I can solve that red equation for h and perform a substitution on h. Now, looking at it, it's quadratic on x, and I don't want to try to have to solve that. So I'm just going to solve that red equation for h. And when I solve that red equation for h, I get that 4xh equals 108 minus x squared. Divide by 4x, I'm going to get that h then is equal to 108 minus x squared divided by 4x. And now I can take this, perform a substitution there, and have volume be a function solely of the variable x. So now volume as a function of x is going to be x squared times h, but h is 108 minus x squared over 4x. Okay? And now that I'm going to got that, I'm going to do a little bit of simplification, clean that up for a moment. Okay, so let's see. I think I can get a cancellation to occur here and here. And let's see, what will that give me then? That will give me 108x minus x cubed divided by 4, or if you prefer, 1/4 times 108x minus x cubed. Okay? And then we need to, what do we need to do? We need to maximize this function. And so how do you maximize a function? Well, we're going to take a derivative, find critical numbers, check those critical numbers to see if they are a max or a min by using that first derivative test, looking at the increasing and decreasing nature to the left and right of those critical numbers. Right? So first things first, I need critical numbers. But to get critical numbers, I need v prime. That is the first derivative. Right? The 1/4 is the coefficient, so it's going to come along. The derivative of 108x is 108 minus 3x squared. Okay? So then my critical numbers, okay? Critical numbers are when that first derivative does not exist or when it's equal to 0. Given that it's just a polynomial, there's going to be none of the does not exist. And let's see, when is it equal to 0? Well, it's equal to 0 when 108 is equal to 3x squared, which is when x squared is equal to, what's 108 divided by 3? 36? So that's when x is equal to 6. Now you'll notice that I ignored the negative solution. I ignored the negative 6. And why did I ignore the negative 6? Well, this is somewhat of a real-world example. X is a length measurement of the base of the box, so negative 6 is not a number that makes sense to me. So now that I've got that critical number, okay, I'm going to test. Okay? I'm going to test slightly differently, though, because I'm putting a hard stop at 0. And the reason being is negative numbers don't make sense. And that's going to give me only 2 intervals to test. Okay? I'll test interval number 1. I'm going to pick the number 1. I'm going to take that number 1 and put it into that first derivative, and I'll see whether that makes it positive or negative. So v prime of 1 is going to be 1/4 times 108 minus 3, which is equal to a positive number, which means that on interval number 1, we have an increasing function, which is what we're hoping for, because what was our job? Our job was to maximize the volume. So if this is our critical number and we want that to represent a maximum, it better be increasing to the left and decreasing to the right. So let's check. Interval number 2, I'm going to use 7 just because I can. Right? And so then what is v prime of 7? V prime of 7 is 1/4 times 108 minus 3 times 49. Okay? 3 times 49 is 3 times 50 minus 3. So 3 times 50 is $1.50 minus 3 is $1.47. 108 minus 147 times 1/4 is a negative number. A negative number means that we are decreasing on that interval, and so if we are increasing to the left of our critical value and decreasing to the right of our critical value, that means that our critical value, our critical number here, 6, represents a maximum. So that means that our volume is maximized when the base is 6 inches by 6 inches, and the height, because we're talking about a box, is, and how do I find the height? How do I get the number that I'm going to put there for the height? Well, I'm going to go right back up here and say, what does this tell me? Well, that tells me that the height is equal to 108 minus x squared over 4x, but we know that x is 6. So what is the height when x is 6? Well, the height is equal to 108 minus x squared over 4x. Did I get that right? Yeah. Plug in a 6 and see what happens. So that's going to be 108 minus 36 over 4 times 6. 4 times 6. What's 4 times 6 is what? 2 times 12, 24? 108 minus 36. Well, 108 minus 30 is 78. 78 minus 6 is 72. So we get 72 divided by 24. 72 divided by 24 is 36 over 12, which is 3. So the height is 3 inches. All right, now I'm going to go back. The last thing I'm going to do is I'm going to go back and make sure that I answered the question that was asked. Because they could ask me what is the maximum volume, or they could ask me what are the dimensions of the box. Right? And the question is, and there's the question mark, what are the dimensions that will produce a maximum volume? And so the dimensions are the volume will be maximized when the base is 6 inches by 6 inches and the height is 3 inches. So this is an optimization problem. This is a classic optimization problem. Finding the maximum volume of a box. All right? So let's just walk back through it and see what we did again. If my job is to maximize volume, I write a volume equation. If I can maximize it as it is, I take a derivative, critical numbers, and I'm done. If I can't maximize it because it has extra variables, I find some other piece of information, write some secondary equation to do a substitution to turn 2 variables in this case into 1 variable. Once I get it down to 1 variable, then I do what I learned in the section on extrema. I find derivatives, I find critical numbers, I test intervals, but I make sure that I only test intervals that make sense. Okay? There are some problems, some optimization problems where negative numbers will make sense. There are some optimization problems where negative numbers won't make sense. There'll be some problems where there will be a fixed lower limit. There will be other problems where there will be a fixed upper limit, okay? A highest value. Okay? Because I'm pretty sure that there is some number. If we go back and look right here, I'm pretty sure that there's some number that if x gets bigger than, it's going to make that height go negative because of this equation right here. If x gets larger than the square root of 108, then that function will make a negative height, and negative height doesn't make sense. So there is some number over here on the high end that'll make height go negative. So technically, I should have stopped this interval somewhere. In fact, I should have stopped this interval up here at the root of 108, which is roughly 10 point something, right? And make sure that I only check or only use numbers that are smaller than that when I check that second interval. Right? Because outside of 108, the square root of 108 would be, this doesn't make sense, so I really can't use it. All right, so increasing, decreasing, maxes and mins. Oh, let's make it harder. Let's wrap some words into it. All right, we have another problem down here that we'll take a look at, optimizing area. But I just want to talk about the guidelines. Right? The guidelines for solving them. These are the steps that the text gave us. Right? First step is to identify all given quantities to need to be found and make a sketch. Now, in the last problem, I didn't have to do that because someone did that for me. They drew me the picture. They labeled the dimensions, x and h, and all that. We write a primary equation. The primary equation that we wrote there was the volume equation. Okay? The secondary equation was the surface area equation that we used to do the substitution. And this step 3 right here is only if you need to. Okay? this is what we were just talking about a moment ago, this idea of making a feasible domain. And the idea of a feasible domain is just saying, what numbers make sense? Do negatives make sense? If so, test them. If they don't test them. Is there a largest value? Like we said, the square root of 108. Don't test numbers bigger than that because that doesn't make any sense, right? And then determine the desired maximum or minimum value by calculus techniques. Basically what they're saying there is either use the first derivative test or the second derivative test to find that max or that min. So critical numbers, testing intervals, seeing if it goes up and down to find a max or down and up to find a min. Right? That's what we did. This is just the fancy way of saying it. Found a primary equation, volume, that we wanted to maximize. We found a secondary equation, surface area, that we used to do a substitution to turn two variables into one variable. So our primary equation would have a single independent variable. And then we found feasible domains. We made it work doing what we had to do. Right? All right, so let's see. Example number 2, example number 3, example number 4. I'm going to stop this video because we're at 16 minutes, and I'm going to come back and we'll take a look at example number 2 and video number 2. See you back here for part 2.